Hi everyone. Today we're going to be doing our notes on 2.7 combining functions. In this section, we're going to be doing all four operations on functions, adding and subtracting, multiplying and dividing functions. And we're also going to be composing functions, so f of g of x or g of f of x. So I just want to start with looking at some definitions. If I have this notation f plus g of x, this is the same as f of x plus g of x. We simply add the expressions for f of x and g of x. Likewise, f minus g of x is equal to f of x minus g of x. We take the difference of the expressions. F times g of x, again, is the product of f of x and g of x. And finally, f divided by g of x is equal to f of x divided by g of x. And that's given that g of x is not the constant function, g of x equals 0. Compositions of functions, we're going to use this notation, f o g or f of g of x. This is saying take g of x and use it as the input of f of x. Okay, so let's see what this means practically. Here we have example 1, given f of x is equal to 4x squared minus 2x and g of x is equal to 2x, find the following. We'll start with letter A, which is f of g of x. Remember, this is the same as taking f and then plugging in g of x as the input. Okay, and actually I'm going to use a different color here. So if you have a different color, you can follow along with me. So say we have f of x, which is in red, and then we'll do g of x, which is in blue. All right. So then if we're composing these functions, we're going to take g of x and plug it in for f of x. So here is g of x, and then our function f of x is this right here. Okay, so now let's go ahead and we're going to say f of x. So writing out f of x, I have 4x squared, and I'm just going to write out x squared and then minus 2x. But instead of writing out x, our input is no longer x, it's g of x. So instead of plugging in x, I'm going to plug in g of x, which is equal to 2x. So anywhere that I see x, I'm going to plug in 2x. All right. Now let's go ahead and simplify this expression. Here we have the quantity 2x squared is equal to 4x squared. So we have 4 times 4x squared. And then minus, well, 2 times 2x is 4x. And then we're going to simplify further. We get 16x squared minus 4x. Okay? This is a quadratic function or polynomial function. The domain for all polynomial functions is all real numbers or negative infinity to infinity. Okay? So now let's compose g of f of 3. Now we'll start, this is just like finding if I were to start with f of 3, and then we're going to plug it into g of x. So whatever our output is for f of 3 is going to be our new input for g. So we'll start with f of 3. This is equal to, if I plug in 3, we have 4 times 3 squared, and then minus 2x, or minus 2 times 3. Now that becomes our input of g of x. Now remember, g of x is 2x, so our output of our f of 3 becomes our x, or our input of g of x. So we have 2 times all of that. So let's go ahead and evaluate. So on the inside, remember PEMDAS, we have 3 squared is 9, times 4 is 36. And then minus 6. And I'll go ahead and write that in blue. 2 times 6 minus 36 minus 6. This is equal to 36 minus 6 is 30, times 2 is 60. Okay. Another way you could do this is just first evaluating f of 3. So if I were to just do f of 3, we would get 4 times 3 squared, and then minus 2 times 3. And we have 4 times 3 squared is our 36. That's our 9 times 4. And then minus 6. And that's equal to 30. Then what you would do is evaluate g of 30. So that becomes your new input. So g of 30 is simply 2 times 30 is equal to 60. So either approach you take will get you the same answer. You can either do it all in one fell swoop here and just plug in f of 3 into the g of x function. Or you can just simply evaluate f of 3 first and then plug that output into the input of g. All right. So the domain here, well, this is just a single value here. So the domain here is just the discrete value 30 because we only evaluated g of f of 3. So not really much of a domain. Otherwise, it's the same domain, all real numbers. All right, so example 2. Here we have h of x and j of x, h plus j of x. So we're going to take h of x, which is 3 over x. So I'm going to do h of x in red. We'll do j of x in blue. So then, here we go. We're going to say h of x plus j of x. So j of x is 4 over the quantity x minus 2. And in order to simplify this, I need to find a common denominator. So our common denominator is simply going to be the product of x and x minus 2. So we have x squared minus 2x. So we're multiplying. I'm not going to show that multiplication yet. We can just write out that product. And then in order to get that common denominator, we need in the numerator of our left-hand term should be multiplied by a factor of x minus 2, the quantity. So we have 3 times the quantity x minus 2, and then plus 4 times x. Okay, let's go ahead and simplify. So now we can go ahead and simplify our denominator, x squared minus 2x. In our numerator, we get 3x minus 6 plus 4x. And we can simplify further, 7x minus 6 all over x squared minus 2x. So our domain here, you may remember last year from rational functions, that the domain is anything, the restrictions on the domain, I should say, is anything that causes the denominator to be equal to 0. So I'm looking at this step right here. Values for x that cause the denominator to be equal to 0 are 0 and positive 2, because that causes one of our factors to be 0. And we know from the zero product property, if the product of factors is equal to 0, then one of those factors must be equal to 0. So numbers that make this denominator 0 are 0 and 2. So our domain is from negative infinity to 0, and we don't want to include 0. And then union 0 to 2, we don't want to include 2. And then union 2 to infinity. Okay, so all real numbers except for 0 and 2. Now let's take the product, h times j of x. So first we're going to write h of x, which is 3 over x, and then times j of x, which we know is 4 over x minus 2. And let's go ahead and expand that parenthesis. All right, so then the product, we simply multiply straight across, so we get 12 over, and we get x times the quantity x minus 2, or x squared minus 2x. The domain is the same thing, so from negative infinity to 0, non-inclusive. From 0 to 2, non-inclusive. And then from 2 to infinity, again, non-inclusive. All right? And let's go ahead and circle our answers too. There we go. Okay. On to the next page. Let's go ahead and use these functions below to find each of the following. First, we have f of x, the equation 3x squared. We have h of x, the equation x plus 1. J of x, the graph here. And b of x, the table of values. So first, f of h of x. So we're going to take h of x, and we're going to plug it in for f of x. So our input is going to be the quantity x plus 1. And we're going to plug that into what f of x is, which we know to be 3x squared. So instead of writing 3x squared, I'm going to write 3 times the quantity x plus 1 squared. All right? So the quantity x plus 1 squared is x squared plus 2x plus 1. Careful, that's a perfect square trinomial. Remember that middle term, 2x. And then distributing that 3, we get 3x squared plus 6x plus 3. And that's our answer. For number 2, we have j of b of 0. So again, this is taking b of 0. I'll go ahead and write it this way. And then we're going to plug that output as the input of j. So b of 0, looking at the table of values, the function evaluates to negative 4. Negative 4 is now my input for j. So I'm going to look at the graph and plug in negative 4 for x. What's my y value or j of x value? The answer is 1. So I'm just going to go ahead and write each of those steps. J of b of 0 is equal to j of negative 4, which is equal to 1. Now we have number 3, j times f of negative 2. So we're going to take j of negative 2, and we're going to multiply it by f of negative 2. So j of negative 2 is equal to, well, looking at the graph, negative 1. And then times f of negative 2. So we're going to plug in negative 2 into the expression for f. So 3 times the quantity negative 2 squared, which we know is negative 2 squared is 4 times 3 is 12. So negative 1 times 12 is negative 12. Okay. Number 4, h of f of x. So this is like number 1, but now we're switching the order. We're plugging in the input of, we're plugging in the output of f of x into the input of h. So remember, h was x plus 1, and then f of x was 3x squared. So we're going to plug in f of x in for x in the function h. So we have 3x squared plus 1. And there's nothing to simplify here. It just stays as 3x squared plus 1. Number 5, b of h of negative 5. So we're going to first evaluate h of negative 5 and then plug that into our function b. So h of negative 5 is equal to, that would be negative 5 plus 1. So that's equal to negative 4. And then we know b of negative 4 from the table of values is equal to 3. So b of negative 4 equals 3. Okay. Number 6, j divided by b of 3. So we have the same as j of 3 divided by b of 3. J of 3, we look at the graph. J of 3 is equal to 1. And then b of 3 from the table of values is negative 3. So we have this is equal to 1 over negative 3, or simply negative 1/3. All right. We got a few more. Number 7, f over h of x is the same as f of x divided by h of x. So remember, f of x was our 3x squared, and h of x was our x plus 1. These are our two equations. Nothing to simplify here. This is it. We can't reduce or factor out anything because our denominator is separated by addition. We can't do anything there. Our whole factor is x plus 1, which is not a common factor in the numerator. Number 8, f minus b of 0. So we're first going to take f of 0, and we're going to subtract b of 0. So again, f of 0 is equal to 3 times 0 squared. And then b of 0, looking at our table of values, is negative 4. So we're going to subtract negative 4. Well, we get 0 squared is 0 times 3 is still 0. And then minus negative 4 is the same as adding positive 4. So 0 plus 4 is 4. And last but not least, h plus j of 1 is the same as h of 1 plus j of 1. So h of 1, h was our x plus 1. So we have 1 plus 1. And then our j of 1, let's take a look at our graph here. J of 1 is equal to 1. So then we have 1 plus 1 plus 1, which is equal to 3. All right. So these have been our notes on operations and compositions of functions, just called combining functions. We're going to get a lot of practice on this, so we'll see you tomorrow. Have a great day, everybody. Goodbye.